Greetings, chemistry students. Today, we're going to talk about one of the most important equations that's ever been discovered in all of chemistry. It's called the ideal gas law. And it looks pretty simple when we look at the equation. It says PV equals nRT. So it's an equation that has 5 different variables in it. But solving it is just going to involve some very simple algebra. There's nothing super complex. It's 2 things multiplied together on one side, 3 things on the other. So P is pressure in this equation, V is volume in liters, T is temperature, and then N is number of moles. And I know that some of you don't like moles, but they're back again. N is number of moles. And the other thing, R, is our ideal gas constant. Now, what's unique about the gas constant is you may remember that pressure we can measure using atmospheres, kilopascals, millimeters of mercury, which is the same thing as torr. So if we can use 3 different units for pressure, we need some way to account for that in our equation. Otherwise, we're going to come up with 3 different answers. And so we actually have 3 different versions of the ideal gas constant, which depend on pressure. And if you have your reference tables, the gas constant is found on the first page. It says gas constant, and it gives you the gas constant in those pressure units. And they're kind of weird, but it's either 8.314 liters kilopascals per mole Kelvin, 0.0821 liter atmospheres per mole Kelvin, or 62.4 liters millimeters of mercury per mole Kelvin. The units are kind of weird, just so all of your other units in the equation cancel out. And as you might guess, your temperature needs to be recorded in kelvins, and your volume has to be in liters. Now, what's significant about this equation is for any gas, if you know its pressure, its volume, and its temperature, which are 3 things that are very easy for chemists to measure, then you can know how many moles of gas there are. And then based off of Avogadro's number, you know how many moles of gas there are, you know how many molecules of gas there are. And the thing about this is it doesn't matter which gas you're talking about, the equation stays the same. And this is what the Italian scientist Amedeo Avogadro actually figured out, was that under the same set of conditions, equal volumes of gas contain the same number of gas particles. Which then means if you know how many gas particles you have, if you can figure out a way to figure out how much that gas weighs, then you take how much the gas actually weighs, you divide it by how many moles you have, and then what you have figured out is the molar mass of the gas. You know, those numbers that appear on the periodic table. And that's exactly how a lot of this work was originally done. And later on, I'll show you a demonstration of how this can actually be accomplished in a lab. It's something you can't really do at home, but I'll kind of show you the concepts behind it. It's pretty cool. So that's the only slide of notes we're going to look at today. We'll work more with the ideal gas law tomorrow and Monday. So we're going to look at some problems here. So our first problem says, how many moles of gas are contained in 0.89 liters at 21 degrees Celsius and 750 millimeters of mercury? So we're trying to find N. That's a typo. That should say 0.89 liters. So that's our volume. 21 Celsius is a temperature, and 750 millimeters of mercury, that's obviously our pressure. So the equation once again says PV equals nRT, or we can kind of rearrange this to say that N equals PV over RT. That's just some basic algebraic manipulation where we take the R and the T and we move them to the other side. So now we just need to plug in the numbers. Our pressure is 750 millimeters of mercury. Our volume is 0.89 liters. Our gas constant in millimeters of mercury. If we look on our reference tables, it is 62.4. And our temperature is not 21 Celsius. We need to convert that to kelvins, which, if we remember on page 3 of our reference tables, we do that by adding 273. So 273 plus 21 is going to be 294 kelvins. And so we take 750 times 0.89 divided by, in parentheses, 62.4 times 294. We get 0.036 moles. For the second problem, we're going to work it pretty much the same way. We're solving for moles again, where N equals PV over RT. Where we've got volume, temperature, pressure. What I would suggest when you're watching this video is that you pause it and try to work through these problems on your own first to see if you got the hang of it before you watch me actually work it out. But it's up to you how you want to actually take advantage of this opportunity. But to solve for moles, it equals our pressure, which is 2.50 atmospheres, times the volume, which is 10 liters, divided by our gas constant in atmospheres is 0.0821 liter atmospheres per mole Kelvin. I'm going to actually show you how these units cancel out on this one. And then our temperature is 25 degrees Celsius plus 273, which is 298 kelvins. Now, what's interesting about the units is we have atmospheres on the top of our equation and atmospheres down here. We have liters on top, liters down here. Then on the bottom, we have kelvins and then kelvins on the bottom of that fraction. So our units are going to come out to be something divided by moles. And if you divide by something and divide by it again, you're multiplying by it. So our units come out to be moles, just like you would expect. So then we take our calculator and we do 2.5 times 10 divided by, in parentheses, 0.0821 times 298. And I'm coming up with 1.02 moles. For the third problem, we are now solving for volume. So our equation of PV equals nRT can be rearranged to say that volume equals nRT over P. So now we plug in moles, which is 3.75. Then we need a gas constant. Now our pressure is measured in torr, and there is no gas constant in torr. But if we remember that millimeters of mercury and torr are the same thing, then all we have to do is use the gas constant for millimeters of mercury. So we're going to use the 62.4. One other thing is, please do not confuse the gas constant with standard pressure. That's an easy mistake to do. The gas constant R and what standard pressure is for doing gas law problems, they're not the same thing. So please just look at your reference tables, take your time, be careful. For temperature, we need 18 plus 273. 292.3, which is going to be 291 kelvins. And our pressure is 5,000 torr. So we're going to take 3.75 times 62.4 times 291 divided by 5,000. And I'm coming up with 13.6 torr. Sorry, not torr. We're looking for volume liters. Then our last problem is asking us at what temperature will 0.654 moles of neon gas occupy 12.3 liters at 165 kilopascals. So if PV equals nRT, then T equals PV over R times N. Let me fix that here. PV over N R. So our pressure is 165 kilopascals. Our volume is 12.3 liters. Our moles are 0.654. And our gas constant in kilopascals is 8.314. So then we just take our trusty calculator, 165 times 12.3 divided by, in parentheses, 0.654 times 8.314. I'm coming up with 373 kelvins, or if we subtract 273 from that, 100 degrees Celsius. So I hope this helps. Keep in mind, once again, for this last problem, it doesn't matter whether we were working with neon gas or helium gas or oxygen gas or sulfur hexafluoride gas. No matter what gas we're working with, the answer would be the same. That's what's so neat about the ideal gas law. So I've got a few problems for you to try on your own in Google Classroom. Good luck.